Hello, in this video I'd like to go over a Visual Studio Code extension for OSS-Fuzz that can be used to improve the fuzzing workflow and speed things up, and also has a lot of convenience functionalities such as generating code coverage in a very convenient manner so you can track progress continuously. And in this video I will show both how to install the extension and also how to use it to fuzz a project, cJSON, where we focus on how to improve the code coverage. So the first thing I will do is I have VS Code over here. I have introspect.ossfuzz.com here, which I will use to analyze our project of interest. And first I'm gonna install the extension. It's called OSS-Fuzz, and I'll simply just, now it's installed. You click install and that's good. And then next, what I will do is I will select the project we are going to improve. So we will focus on improving the fuzzing of an existing project where we try to get code coverage higher up than it is. What I will do is I will look for the project in here, and I've already picked it. It's called cJSON. We can see that it has 44% code coverage, is quite small, so 2000 lines of code. And it currently has a single fuzzer. So what I'll do is I'll find the repository for this. I will find the repository that holds the source code of cJSON, and I can see that right here in the Docker file. So what I'm going to do is I'm going to clone this project. And then I will simply adjust the fuzzing from this source code of this given project. So we should be good now. Why did it not pop up here? Okay, like that. So the first thing that I will do is I will set up OSS-Fuzz, and what that means is we need to clone the OSS-Fuzz repository, but the VS Code extension will do that for us. And let me just show you here that there's no file currently under temp OSS-Fuzz, but once we have run setup OSS-Fuzz, we can also see the output from the OSS-Fuzz VS Code plugin, and we can see that it sets up OSS-Fuzz in the TMP directory. And we now have the directory, and we now have the OSS-Fuzz repository, which is this repository over here, within our TMP folder. Now we need this folder here because it contains the logic that is needed to build and run OSS-Fuzz projects. So what I will do first is give a quick overview of the cJSON fuzzing. So this is the cJSON repository, and they have a folder fuzzing where you can see that there is a single fuzzer inside, and it performs various operations. I think primarily it sets up a few arguments here based on the data from the fuzz engine, the data buffer here, and then it calls into pass with opts, which is likely the sort of central target of this fuzzer. There is also various other cJSON APIs, and they are likely also targets, but this one will most likely have most of the logic that this fuzzer targets. We have a script here which builds the fuzzers. So we can see that it calls cmake and make, and then it calls cxx, which is clang in this case, which is the compiler of within the OSS-Fuzz Docker images. And it uses that to compile and link the fuzzer, which is then the fuzzer that will be running on OSS-Fuzz. We can also see that the build script on OSS-Fuzz simply calls into cJSON fuzzing /OSS-Fuzz, which is this script right here. So when we want to extend the fuzzing of cJSON, we'll have to adjust things inside of this fuzzing folder. And the convenient part of this VS Code plugin is that you can do all of this just inside of here without having to deal with adjusting, let's say, how the Docker file clones the given repository and so on. When we use the VS Code extension, we will use the local folder that we have here instead of this line right here. And the VS Code extension takes care of that. So the first thing to do is, well, I can show how we can build the fuzzers of this given workspace. And we have a command, OSS-Fuzz build fuzzers in workspace, as follows. And this is a command from the VS Code plugin. So it asks us for the project name of the OSS-Fuzz project name of the project we are working with, and we need to provide that. So we say cJSON, and now it starts to build the fuzzers. As we can see here, we're already performing the cmake and make, it seems like, and successfully built project. And we also can see that the fuzzers in the project are cJSON read fuzzer, which corresponds to this fuzzer right here. Or perhaps more accurately, the fuzzer built by this command, which outputs the fuzzer to cJSON read fuzzer. Now, what we can also do, I want to show you one of the sort of key things that this VS Code plugin can do, which is generate a code coverage report based on the local setup without having to do any work. So we ask for end-to-end coverage generation, and we give the project name as well. And then we have to give the number of seconds that the fuzzer should run to collect the corpus. Let's just give 10 seconds now. And now what the VS Code plugin will do is it will build all of the fuzzers of cJSON using async mode. And then it will it will run each of these fuzzers for 10 seconds, collect the corpus, and then it will use that corpus to generate code coverage HTML reports that we can then monitor starting a simple HTTP server. Then we can monitor locally to watch the code coverage of our local setup. This is super important when developing fuzzers locally. So we can see that it's successfully passed here, and it now gives us a command, load coverage report with the following command, and we'll do that. There you go. So now we have a web server running on 8.0.8, and I have a window open here. And now we have a code coverage report giving, a code coverage report based on our local setup, instantly created. What we can do is we can start to identify the limitations of the existing setup. And to do that, I will simply look at the code coverage report of the cJSON project, and we can do that as follows. And it's a fairly small project, so we can quickly go over the full cjson.c file and simply just scroll around, look a little bit at where is there a lot of red, and we can see, okay, so there's a lot of red right here. That's probably where we have to look. So we can see that there's a lot of various crate functions that are not being fuzzed. This is likely because the existing fuzzer is only sort of focusing on the parsing logic and not so much of some sort of creating JSON projects. And then we also have some helper functions by the looks of it. And we have a large function here, cJSON compare, and we have a large function here, cJSON duplicate. So I think these are the functions that I will be going for. cJSON compare is likely a good initial target because it takes two cJSON objects, and then it has a single bool argument, whether it should be case sensitive or not. So what we potentially can do is we can take the existing fuzzer, which passes raw data into a cJSON object here, and then we can simply see if we can pass two buffers correctly into two different JSON objects, and then we can call compare in order to trigger all of this code. So that's what we will be doing. The way I'm going to do this, so now I'm going to also show how sort of fast it can go to test the addition of a new fuzzer using the VS Code plugin. So first, I'm going to copy this file. I'm just going to change it a little bit. I'm going to say cfuzzer read compare, and let's make it a C++. Let's make it a C++ function. Or sorry, C++ code. And this is because I want to use some helper logic provided by libfuzzer. So let me just type this in. Let's leave this. So what we want to do is we want to only call this function twice with 2 different buffers, and then we will take the return values if they are non-null. We want to pass those into cJSON compare. So let's make a cJSON and then also a b cJSON as follows. Do like this. B cJSON, and then we want to include. We want to use the fuzz data provider provided by libfuzzer. And let's just delete all of this thing we don't care about anymore, like this. As follows. So now we are seeding this fuzz data provider, which is something provided by libfuzzer, and we are going to use that to create, to like conveniently create fuzzer seeded data. So we will do like this: payload 1 equals ftp.consume random length string. Let's also just have a payload 2. Okay. And then let's do as follows. We'll pass this char pointer, the seed string of the payload 1, and then as follows. And then this is it's an int, but I think it's actually a boolean if we look at this option here. So we can just use the following. Oh, let's actually leave this. Let's just say we always require termination. That should be fine. Okay, so now we have 2 AJSON and we have 2 cJSON objects, and what we can now do is we can say if AJSON not equals 0 and BJSON not equals 0, then we're going to pass this into cJSON compare. And here we can pass this boolean case sensitive. Let's assume we can just do consume bool as follows. Okay, so this should be able to trigger the cJSON compare function. And we also have to clean up here. As we can see down here, we have to delete as follows. Okay. And we can now, let's just remove all of this logic because we don't really care about that. We only care about the compare function. And that means we also don't care about formatted and buffered. Let's delete those. And we also don't care about minify. Let's delete that. And required termination, we also don't care about. In fact, we don't care about any of this. Okay. So I think that should be good. What we now have is we have a fuzzer that will create a fuzz data provider using the data provided by the fuzzing engine. And we then use this fuzz data provider to create 2 random length strings. And each of these random length strings are passed into cJSON parse functions. And if both of them succeed, aJSON not equals null and bJSON not equals null, then we compare the 2 cJSON objects created. And that should trigger code coverage of this cJSON compare function. So what we now need to do is we need to adjust the OSS-Fuzz.sh to also compile our fuzzer, our new fuzzer. And in this case, we just do cJSON read compare and cpp, and then we need to output it correctly. And what I will do now is I will first test if it actually works using the VS Code plugin. So we have a function here called test specific fuzzer, and we can say the project name is cJSON, and then we need to give the fuzzer name, which is the binary name that we output to out, which is here. So it's cJSON read compare, and this will build our fuzzer and then run it for a few seconds to ensure that things are actually working. And if things are good, that means we can start to generate code coverage. It seems like it's running and no problem, which is nice. So the next step for us is to generate code coverage report in a way where we can sort of validate that the compare function is also being hit. Let's just wait until this terminates. So it ran for 21 seconds. It's probably set, the timeout is probably set to 20 seconds. And indeed, the fuzzer was running fine. So now what I will do is I will generate end-to-end coverage of cJSON, and I will just run each fuzzer for 10 seconds. That should go quite fast. So now what the VS Code plugin will do is it will build the whole setup again. It will run both fuzzers to generate code coverage, and what we can then use that for is we can assess whether cJSON compare is being hit and analyzed, and if that's the case, then we can just continue to essentially tackle the next function to be analyzed, and until we have covered all of the logic we need to cover. And as we can see that there is quite some logic. I think the duplicate function is another function we can easily tackle, assuming that it just takes a valid cJSON object. We should be able to hit that function quite fast as well. Okay, so this finished, and we now get the command to run the coverage server again, and we just simply run it, and we can just update this to find the exact same place. And this did not work. Why did it not work? cJSON read fuzzer, so our fuzzer was not put out there. Did I miss something? Read compare. So I just realized the mistake, and well, we are looking at the OSS-Fuzz code coverage report, whereas we should be looking at the local code coverage report. So let's just ensure we're doing that, which is simply going to this directory. Oh. Okay, so now we have the local coverage report, and we can already see here that the code coverage is 46%, whereas the OSS-Fuzz actually has 44%. So we have already and 44.52 of the cJSON folder, or sorry, source code, whereas the OSS-Fuzz one has 42.95. So we can already see we have actually increased code coverage by 2%, and we can go down to the cJSON compare, which should be around here. Here, cJSON compare, and we can indeed see that we had code coverage of this function. There are only very few hits on the function, and that's because we only ran the code coverage generation for 10 seconds each of the fuzzers. So what I will do is I will make one more change, in particular to also make sure we have the cJSON duplicate function in our fuzzer as well. And the way I will do that is I will say if a JSON not equals to 0 to null, we will make a new JSON object equals to cJSON duplicate, and we'll just use a JSON here. And let's say we don't really care about whether it's recursive or not, and then we do if new JSON not equals to null, we'll do cJSON delete. Okay, so this should give us code coverage of this cJSON duplicate function as well, and we're going to just test it quickly. So let's say we just run test specific fuzzer, and we say cJSON, and we say cJSON read compare, and it's going to run now. So it's building, and then it will run our fuzzer for 20 seconds, and if all works well, then there will be no complaints, and it is indeed running well. So what I will do next once this finishes is I will take the code coverage generation command again and run it for even longer periods of time. So let's say 30 seconds or 45 seconds each fuzzer, and then we will see how much coverage gain we actually have in our local version of cJSON. So it finished, command ended. So let's run end to end cJSON, and let's say 60 seconds each. And I'll pause the video while this is running, and then we'll see the code coverage generation afterwards. So the code coverage generation now finished, and we can simply relaunch our web server. And now we can just update here, and we can see that cJSON duplicate is indeed analyzed now, and the same with our compare function. You can see we have a few more hits. Before we had 10 or so. There's still some logic for it to analyze, but if we then try and look at the code coverage, so now we have increased it from 42 in the one on OSS-Fuzz to 40, almost 48 now. So, and obviously we will get more coverage once our fuzzers run for longer, simply because the functions that we target are not at all fully explored yet. So, now I want to show a thing in another feature of the VS Code extension, which is you can redo the exact same command as previously, which is very convenient when just focusing on improving the logic of your fuzzer, and for example having to run the code coverage generation without having to give the project name or the seconds again as arguments to the end-to-end coverage generation command. So let's say we want to check the code coverage of this fuzzer, but we have made a mistake in our we have an error in our fuzzer that means it won't build. Then we say cJSON is the project we want to have coverage for, and let's just say 5 seconds. And this is now running, but we can see that it should fail building, and it will. And we can see here that the error was indeed found. There is an error here, and it's a syntax error, and we'll just clean it up. And then what the VS Code extension can do is redo the previous command with the exact same setup. So inputs to the command in the exact same manner. And now that runs the code coverage generation, which can be used for sort of significantly increasing the development time needed to improve your fuzzing. Okay, so at this point we have improved our fuzzing setup by a fair amount, and what we next can do is we can look a little bit more at the functions that are not being analyzed. So there's a lot of, so here we have some categories of cJSON is false, is true, is bool, is null, and it looks to check some sort of type of a cJSON item. So we can probably call all of these functions on our various objects here. And we have some functions related to creation of various cJSON objects, float array, double array, and whatnot. And indeed also many other create functions. None of them are being analyzed. And what more do we have? We have some replacement functions that are not being analyzed. And we have some functions related to adding objects to objects, add number to object, add bool to object, add false to object. And the assumption must be that if you have a valid object here, then you can have an arbitrary string here, meaning this should be seeded by the fuzzer if we want to fuzz this function. And the same with these other functions. We could probably create something a little bit interesting that would call these functions in a manner that would sort of an arbitrary sequence with arbitrary values to ensure that any sequence of inputs to these functions can be still valid, as long as we ensure the sort of contract with the function is satisfied by the fuzzer. Those seems to be the main functions, with a little bit here at the top, but much less. And if we do that, if we create a fuzzer for that, let's see how much code coverage we can get, and hopefully we can get it a bit higher than 47%. So I'm going to just do that while I pause the video, and then I'll run the code coverage generation again to see how fast we can get it up. Okay, so I have this fuzzer here, which is an extended fuzzer, I called it, and it hits all of the logic, or a lot of the logic that was missing in the cJSON library. So we have a lot of these is functions, a lot of the create functions, creating various objects and adding various objects to existing cJSON objects, as well as some printing logic. And it's not the most ideal fuzzer in the sense that you'd want to ensure that these were called in sequences of each other rather than just once in the fuzzer. So you'd have like a sort of, let's say you had a for loop which considered all of these to be operations, and then you would ensure that each of the various sequence operations are possible and so on. But this is still useful for getting code coverage up. It's useful for exercising the code, perhaps not with the highest level of entropy, but it's still a really good start. Before submitting this to upstream, I would change it a little bit just to ensure that it works in the optimal way. I added this fuzzer to the cJSON extended fuzzer, to the OSS-Fuzz build script, which you can see here. And what I will do now is I'll simply run a test, cJSON and this one, and then I'll see if it runs successfully, and if so, I will launch a code coverage generation for a lot longer than previously, and we can see it is indeed running well. So that's good. And what we'll then do is we are going to run code coverage generation again, but let's set the runtime of each harness to 10 minutes or so, and then we can get a much more true estimate of how much code coverage our new fuzzers have. Okay, so let's run the end-to-end coverage generation command. Let's say cJSON, and let's just say each fuzzer should run for 600 seconds. Okay, so now all of our 3 fuzzers will be built and run to collect code coverage, to collect corpus, and then we'll run then the VS Code extension will run the code coverage generation routine again. I'll pause the video while this is running, and then we'll resume afterwards. Okay, so this is now finished, and we can look at our new coverage report using the command given, and we can just update the browser here, and we can see that we got to 73.4%. So that's a nice jump from the original 42% in OSS-Fuzz, and we can see that there's still a few places with red, but down at the bottom, which used to have a lot of uncovered code, we have a lot more code coverage now. And in particularly, often the code that's not covered are code within existing functions rather than entire functions not being executed. We still have a bit of various functions here that are not being executed, but significant increase, 30% increase in code coverage. And we use the VS Code extension to make it fairly easy to test and experiment with the new additions we have. So that's the end of this video. We showed how the OSS-Fuzz VS Code extension can be used to for conveniently developing and extending fuzzers of an existing project. It makes it a lot easier to just focus on developing from within the repository or folder of the source code of a given project, and you don't have to think about interacting with the OSS-Fuzz infrastructure, the help.py script as much, and you have these kind of more extensive workflow features such as generating code coverage with a single command. So the VS Code plugin exists, the source code for the VS Code plugin exists in the OSS-Fuzz repository here. So if you want to add or change or anything like that, please just submit pull requests to I think the way to go is to submit a pull request to OSS-Fuzz, and any issues as well can just be put there. So finally, I think to say is that the plugin has a lot more commands. Many of them are used for speeding up workflows, including stuff such as creating function templates very fast. So there's a lot of various fuzzer harness recipes and so on that you can use, as well as other forms of CI-Fuzz. It's easy to set up CI-Fuzz using a feature from the VS Code extension and more. Finally, a last word is that it works really well with the cJSON project, but it might not always work well depending on, for example, where the logic for interacting with OSS-Fuzz is. So let's say in the cJSON project, the build file simply calls into the OSS-Fuzz.sh in the cJSON repository, but this may not always be the case, and then you might have to do some adjustments in the build.sh when you are modifying the fuzzers of a given project. So I think that's it for now. I hope to make more videos with some of the further features, and hopefully also make videos once the VS Code plugin has even more capabilities. But that's it for now. We showed the VS Code plugin. We showed how to take the code coverage from 42.9%, which we extracted from the introspector OSS-Fuzz.com, and how we could take that up to a total of 73.4%, which is a nice 30% increase in code coverage. And the remainder we will probably not pursue, but we will submit these fuzzers upstream after a little bit of beautifying the code. So that's it. Thank you very much.